Hey y'all, welcome back. Today we are working on our homework, which is going over several different situations is going to require at some point using a logarithm to solve these real world problems. So the first one says the number of farms in Iowa in thousands can be modeled with this function where t is the number of years. So first it's asking, has the number of farms been increasing or decreasing since 1980? So if we look closely at this function over here, the two numbers that we see are the 19, which is going to, or the 119, which is the number of farms in thousands in 1980, basically saying in 1980 there's 119,000 farms. And since we're multiplying by a number that's smaller than 1, we can say that the number of farms is decreasing. So the way we probably want to word this is to say the number of farms is decreasing since 1980 because 0.987 is less than 1. Okay, so basically we're multiplying by some number smaller than 1 that's going to make the overall number decrease. So part B says find the number of farms in the year 1980. So that's going to be our initial amount here since this is when our scenario starts. Don't say 119, it's 119,000 farms. So I'll say there were 119,000 farms in 1980. Then it says find the number in the year 2000. So what we need to do is we need to plug in the appropriate value for t, and then we'll calculate this out. So let me pull up the calculator. Let's see here. There we go. And we will do, scoot this over so you can see. Oh, scooting the wrong thing over. Let's move this over so you can kind of see what I'm doing here. So we're going to do 119 times 0.987 to the power of t. Now here, if our initial time is 1980 and we're interested in the year, let's see, what year was that? 2000, that's going to be 20 years since 1980. So we're going to raise this to the 20th power. Okay, and all right, so based on this, we can say that there were approximately, we are going to round here, this is based on the model, 91,599 farms in 2000. So again, the way that we calculated that, just to kind of put that in here somewhere, was 119 times 0.987 to the power of 20 is approximately, where's my approximate symbol? I know it's in here somewhere. There it is. It's approximately 91.599. Okay, and that's how we're getting this answer. Okay, so it says, according to the model, in what year was the number of farms about 80,000? So this is where we are really going to get started with the solving. We're going to set up our equation, except our unknown is going to be t, and our output is going to be 80,000. Or I guess it'll really just be 80, because our function is defined in terms of thousands. So let's see here. We've got 119 times 0.987 to the power of t, and we want to know when is that going to be 80,000. So we're just going to put 80 there. Okay, so to get a good value here, we're going to first divide both sides by 119. So it's going to equal 80 over 119. And I'm not even going to bother trying to simplify that. It's really just not worth it, since we're going to end up putting this in the calculator anyway. Oh, there we go. Okay, I was wondering where all my reds are. None of these really look like the red I'm looking for here, but it'll have to do. Okay, so now to isolate t when it's in the exponent, we're going to use the inverse property and essentially raise both of these, or input both of these as logarithms, where the base is 0.987 of 80 over 119. That is going to be our t-value. And so if we want to approximate what that would be, we would say t is approximately, and this is something we're just going to type into the calculator. So let's pull up the calculator. And to do log base, you're just going to hit math, log base, 0.987, and in here we're going to do 80 over 119. Now just trying to think realistically here. Since there were 91,000 farms in 2000, to get down to 80, I'm gonna guess maybe like 2010. I don't know. It's definitely gonna be after 2000. So let's see what we get. So we get 30. So that's this many years after 1980. So if we want to know like the exact year, then what we can do is just add this to 1980, and we'll get the year. All right. Oh, wow. So in what year? So in 2010. So in 2010, there were approximately 80,000 farms in Iowa. All right, so just want to make sure we're answering the question using the context that's given. All right, so there's number one. Number two says your visual near point is the closest point at which your eyes can see an object distinctly. The diagram shows the near point at in centimeters y at age x in years. So this function can be used to model that relationship. So it says, first, use the model to predict the visual near point for age 10. Okay, so basically all we need to do here is we are going to input 10 into our function for the age. So 3.5 times 1.054 to the power of 10. And let's go ahead and calculate that out. Again, most of these, if not all of them, are going to be calculator problems. So let's go ahead and pull that up. So 3.5 times 1.054 to the power of 10. And all right, so we get approximately 5.922. Okay, so that would be it. That would be the visual near point. Okay, so at age 10, it's like even smaller than all this. So the closest point to where you can see an object distinctly. I guess what this is basically saying is that your vision, your sort of like long distance vision, increases with age at an exponential rate, slowly but surely. Okay, so yeah, so we're gonna say that's it. That's the visual near point in centimeters at age 10. It says at what age does the model predict a visual near point of 22 centimeters? So just by looking at the chart over here, 22 centimeters it looks like is going to be in between ages 30 and 40. Let's get rid of this real quick. Because at age 30 it's at 15 and age 40 it's at 25. So it's probably, if I had to guess, somewhere like 37, 38, something like that. But we want to solve this as an equation. So we're going to say that, when is this going to be 22? So 22 equals 3.5 times 1.054 to the power of x, and we're going to solve for x here. So to solve for x, we're going to first divide both sides by 3.5. So 22 divided by 3.5 is 1.054 to the power of x. And then we can use the inverse property to isolate the x when it's in an exponent like this. and write it as x equals log base 1.054 of 22 over 3.5, whatever that is. That is actually there's probably a better number to use there, but should not be a big deal here. So let's go ahead and pull up our calculator again. Where did it go? There it is. There it is. Okay. So I'm going to hit math, just up arrow twice to the log base, and I get 1.054 for the base, and for my argument, 22, that'd be like 44 divided by 3, whatever that is. But I'm just going to leave it like this and press enter. Okay. Oops. There we go. All right, there you go. Okay, so about 34. Okay, so that's a little bit less than I was expecting, but it is what it is, yeah? So we're going to say that at about 34.953 years of age. So right before you turn 35, you know, we'll say like about 35. If you're just, you know, speaking normally. But if you want to get a more precise answer, that's what it would be. Number 3, okay, we get a nice logistic function here. You plant a sunflower seedling in your garden, and the height after t weeks is given by this crazy looking equation. And it says, find the time it takes for the seedling to reach a height of 200 centimeters. So basically, we're going to plug in 200 here, and we are going to solve for t. So we've got 200 as our height equals 256 over 1 plus 13 times Euler's number to the power of negative 65 hundredths times t. So first things first, I'm going to multiply both sides by this denominator just to really clear up that fraction. So I get 200 plus, so because 200 times 1 is 200, 200 times 13 would be 2600, e to the power of, same power, that doesn't change, equals 256. So at this point, I can now subtract 200 from both sides. Get rid of that 200, and 256 minus 200 is 56. Now I can divide both sides by the 2600. And this probably is reducible. I don't know if it's really worth it at this point. It's not like obvious what it's going to reduce to. I think it may be okay just to kind of leave it like that for now, since we're going to put in our final thing in the calculator anyway. All right, so at this point, we need to use the inverse property. We need to isolate this exponent. Now, it is going to have that negative 0.65t, or the negative 0.65. It's still going to be that coefficient still sticking out there. So, and that's going to equal the natural log of the 256 over 2600. And then as our final step here, we are going to divide both sides by negative 0.65 to isolate t. So t is going to be this number divided by that number. Oh, too much got copied there. Yeah, you're dividing by negative 0.65. So that's going to be our exact answer. That's not a very satisfying answer because we want to be able to say like, okay, well, roughly how many weeks is this, right? So we're going to say that it is approximate. So I'll write it as a statement. Find the time it takes for the sunflower to reach a height of 200 centimeters. So I'm going to say it takes approximately some number of weeks for the sunflower to reach a height of 200 centimeters. And this I'm going to fill in by typing in this statement right here into the calculator. So let's pull that calculator back up. I'm going to make a nice little fraction here with the numerator being the natural log of, well, another fraction. 256 over 2600 divided by negative 0.65. All right. And so we get about about 3 point, what's going on here? 3.566 weeks. Okay, number 4. This is a problem similar to one that we had in the notes. So this is not a formula you need to memorize or anything, just so you know. This law of cooling, it's just a convenient formula for what we're doing here, which is learning how to use logarithms to solve these equations. So first I'll just go ahead and retype Newton's law of cooling so that I can have it to copy and paste. So basically what we're doing here is we want to know how long it takes for a turkey that we have carved to be cool enough for us to actually carve it. So let's see here. We've got T equals T naught minus T sub R times Euler's number to the power of negative RT plus that TR, the surrounding temperature. Okay, so let's start substituting all the values that we know in here. So the T naught, which is the temperature, the initial temperature. Hold up, I think there is a typo here. This is worded kind of funny, but this is going to be the initial temperature, this T naught. I don't really like how this is worded. This is the initial temperature. R is the temperature of the surrounding, and then it's just the T. Yeah, I think the typo here is there's not supposed to be a knot on this. Okay, so T naught's going to be the initial temperature. So the initial temperature here was 180. Okay, the surrounding temperature was 72. We're trying to calculate the time, so that's going to be our unknown. The final temperature, let's see, until the internal temperature is to 100. So, okay, so the final temperature we want to be 100. And the time is what we're trying to find. The rate, the cooling rate is 0.067. Okay, so now our equation is totally set up and we can start to solve. So I'm going to first subtract 72 from both sides of the equation. 100 minus 72 is going to be 28. I guess I can also, on this step, do the 180 minus 72, which is 108. Yeah. Okay, and now I can divide both sides by 108, so I get 28 over 108 equals all this. Okay, and now I can use the inverse property to rewrite this as a logarithmic statement. So negative 0.067 times t equals the natural log of 28 over 108. We're getting very close here. And now I need to divide by negative 0.067 on both sides. So I get t equals this natural logarithm divided by negative 0.067. And this is something I'm going to put in the calculator, very similar to how the last problem was set up. So let me pull up the calculator and we will type it in, the natural log. Oops, let's clear that out. Actually, look, we got a little template going over here. So the natural log of, 28 divided by let's get rid of that 5. There we go. 28 divided by 108. That other 0. Divided by negative 0.067. All right, and so we get approximately this 20.148 number. And so, and then t is measured in minutes. So we can say, as our answer here, the turkey will be ready for carving after approximately 20, a little over 20 minutes here. All right, moving on to number 5. Did we really do? Oh yeah, I guess we did do 4 problems. Number 5, the George River herd of caribou in Canada was estimated to be about 4,700 in 1954 and grew at an exponential rate to about 472,000 in 1984. Use this exponential growth function where P naught is the initial population and P of t is the population at time t to determine k. So basically, it looks like we're going to set up an equation where we solve for k here. So the final population was 472,000. Let's make sure we're writing an equation here. Equals the initial population, which was 4,700. Oh, wow, that's like growing like crazy then. Times Euler's number to the power of k times t. Now here from 1954 to 1984, that is 30 years. So we're going to multiply this by 30. All right, so the first step is going to be to divide both sides by 4,700. Now, I'm not going to totally divide it out. I'm going to, I'm not going to waste time trying to figure out what exactly that is. But one thing I can do just to kind of shrink the numbers a little bit is just, divide both of these by 100. Get rid of some of these zeros. Okay, and then now I can use the inverse property to rewrite this as a logarithmic equation. So I'm going to have 30k equals the natural log of 4720 over 47. And so k is going to be that natural logarithm divided by 30. I'm going to divide both sides by 30 here. So I'm going to go ahead and divide that out. This is where it's time to bust out the old calculator. And so I've got the I'm going to use this again, might as well. The natural log of, get over there, 4,720 divided by 47 all over 30. And let's see, so we're trying to determine k, so that's k. That's it. So k is just basically this number that is part of our function that tells us, how fast these caribou are multiplying. So we're going to just say it's approximately 0.153, and so 3 would round up to 4. Now, I'm guessing we could probably use this to find out, what the population is at other times, and I'm kind of wondering if that's where this is going. Yeah, during what year would the population have doubled to its original number? Okay, so I'm going to go back and, retype this equation. So double its original number. So let's see here. It was at 4,700 on the first year, on the initial year. And so twice that would be a 9400 would be double. And we don't know the time this time, but we do know the k now that we found it. And I think in my calculations, I'm actually going to use the real k so we can get a more accurate number. So when I type it in, I'm not actually going to type in 0.154. I'm actually going to type in, well, I won't really type anything. I'll just go back and reference what we have in the calculator. So anyway, we need to solve for the t, and then we'll add that back to 1954 to figure out what year that actually is. So the first thing we want to do is, to solve for this, is we want to divide both sides by 4700. So 4700, and just like what we did the last one, we'll divide both of these by 100 just to kind of clean it up a little bit. Equals e to the power of 0.154t. Again, this is an approximation. Really, I guess we should have an approximate symbol here because this is not exact. My k value is not exact here. So a little bit, just a technicality here. It's not really going to affect how we solve the problem. But if we want to be, absolutely correct, this is what we got to do. So now we've got 0.154 times t is approximately equal to the natural log of 94 over 47. And I've said this a million times so far, but we're using the inverse property to rewrite this exponential equation as a logarithmic one. So now I'm going to divide both sides by that k value. So t is approximately natural log of 94 over 47 all over that k value. So when I go to divide it in the calculator, since I already have like the legit k value in there, I'm going to use that. If you lose track of it and you have to use this rounded version of k, it's not going to totally throw it off. In fact, what might be interesting to see is if we try it both ways and see, because of the rounding here, we might actually end up with the same answer. But I don't want to take that chance. So t here will be approximately, let's go ahead and type it in. I'm actually going to, actually know what I need to do here. I'm going to save this number and just to sort of stay consistent with what the problem is, I'm going to save it as k. So now I just have to type k instead of this long number. So now I'm going to say the natural log of 94 over 47. Really, this is just like 2, right? It should be double. Over k. So we'll do k, and then if it's worth it, we can go back and check and see what happens if I were to use that rounded answer. So I get about 4.511. So it's this many years after 1954. So if I add that to 1954, I get the year 1958. Okay, so the population would have doubled, or here's a better way to say it. The population doubles from 1954, the initial year, to 1958. Yeah, there we go. Now, just to kind of double check what I was saying earlier, if I were to go back here and instead of like typing k, type like the rounded k here that I've been writing out, the 0.154, I get a slightly different number. I mean, it's not going to affect my year because of the rounding here, but look, you can see the 4.511 is different than 4.500. And I guess this would round up to 4.501. Either way, it's different. So you just want to be really careful with the rounding, and to be on the safe side, don't round until the very end. Okay, save this k value as a constant in your calculator if you're going to have like a multi-step problem like this. Okay, so letter C, if the herd had continued to grow at this rate, what would the population have been in 2010? Okay, so in 2010, we were just, now that we know k and we know all that, we are going to just figure out what this would be. Oops. Now in 2010, that would be, so 2010 would be 2010 minus 1954, just to figure out like what my t value should be. I'm just going to type this in real quick. This probably isn't worth its own step. So 2010 minus 1954. Okay, so 56. So really, my t value here is 56. All right, and so we'll say this is approximately, now this is going to give us the population here in 2010, allegedly, according to this model, and we'll just sort of make a value judgment on it. It's going to, let's see what the number is and see how realistic it seems. If it's a number that seems like it should be within the realm of possibility, we're gonna say, is this? What was the question exactly? Is this realistic? I don't know. Let's see what we end up getting. So I'm actually not going to do the 0.154. I'm just talking while I'm typing. What I really want to do here is the k, to get exactly as close as I can to it. Where's k on here? H-I-J-K. Times 56. Okay, so we get approximately 256,37376. So that would be 25 million. 25 million from 4,700. That just seems kind of high. I'm just going to say 25 million seems kind of high. Probably not realistic. Although, I don't know, maybe it is. It just seems high to me. So I'm not really going to worry too much about, if that's like technically right or wrong. I don't think so. I mean, it just seems too high. 25 million seems too high to be realistic, I think. Maybe that's not realistic. Maybe it is, but it just doesn't really seem too high. I can't spell. Too high to be realistic. There we go. All right, so yeah, I mean, from 4,750 years to 25 million. Yeah, I mean, I don't know. You tell me. What do you think? I think it's too high. All right, let's look at a few half-life problems, and then we're done for here. Oh, it looks like we just got one, and then we got another exponential problem. Number 6 here says that the half-life of radon 222 is 3.8 days. So we can start writing our equation. So our final amount here is going to be, I think we used n for the notes. I'm just going to go ahead and use y because I don't remember what the variable was that we used. I think it was n, not 100% sure. I guess I can go back and check. Yeah, let me just go check. So all right, so yeah, it was n. So here's the formula that I gave you in class. So n, which is going to be our final amount, equals, I'm not sure why n is the letter here. Probably should have chosen something else. Equals n naught, which is the initial amount, times a half, because it's a half-life, to the power of t, which is the total number of years, divided by h, which is the half-life in years. It doesn't necessarily have to be years, by the way. It could be days. Whatever the units are, just make sure you don't have a mismatch here. One important thing, sometimes there's some tricky problems that give like the time in years and half-life in hours, but it doesn't really matter which one it is as long as both of these are consistent, that the t and the h have the same unit of time. So in this particular one, we have, let's see, the half-life is 3.8 days. So that means this number right here is in 3.8, and we're in terms of days. It says how much radon 222 will be left in a 16 milligram sample, so that's our initial amount, after 7.6 days. So I'm going to throw in 7.6, sorry, here. And now I'm just going to throw that in the calculator. So we're going to say n is approximately, this is going to be measured in milligrams, okay? So just keep a heads up. Let's go to the calculator and just type away. So we got 16 times a half to the power of 7.6 divided by 3.8. And exactly 4. How about that? That's great. And that makes sense, actually. Now I actually look closer at the numbers. It says the half-life's 3.8 days, so if we got 7.6, that's 2 half-lives. That means the amount is going to get cut in half twice. So if I cut 16 in half once, I get 8, and again, I get 4. So actually, this is going to be exactly 4 milligrams. How many days until the 16 milligram sample decays to 2? Okay, again, this is almost like a non-calculator problem because of the numbers here. We could probably figure it out. We just, one more half-life will get us there. So what would that be, like 11.4? So I'm expecting 11.4 to be my answer, but for the sake of solving, let's go ahead and set it up and actually solve this out. So yeah, I'm expecting to get a number 7.4 here. So my t is going to be my unknown, and my final amount's going to be 2. So the way you would solve this out, and they're not always going to work out this nicely, so that's why I want to show you how to solve this out so that you kind of get the feel for it. We're going to divide by 16. This is how you would solve it if you can't just figure out, which will be most of the time, over to the power of t over 3.8. Now this 2 over 16 does reduce to 1 over 8, so I'm just going to go ahead and do that now. And now we're going to rewrite this as a logarithm using the inverse property. And so I get t over 3.8 equals log base 1/2 of 1/8. Okay. Finally, I'm going to multiply both sides by 3.8. So I get t equals 3.8 times this logarithm, which I believe we can actually do mentally. But I'm just going to assume that this is going to be a calculator problem. And I'm going to type this in. Now, I'm expecting 3 half-lives here. So 2 half-lives of 7.6, 3 would be 11.4. So let's see if if I know what I'm talking about here. 3.8 times log base 1/2 of 1/8. All right, moment of truth, 11.4. All right, yep. All right, so we're going to say t is 11.4. So 11.4 days. Really like how nicely that worked out. Especially compared to a lot of the solving problems you had to do on the last homework. This is a little refreshing to get a nice clean number like that. All right, so there we go. Last problem here. We're talking about stocks. It says the stock price is initially priced at $40, increases as a rate of $8 per year. So my equation here is going to be y equals, this is not the equation button I wanted. What? Come on. Cammy's kind of lagging on me. So 40 times, it's 1 plus 0.08, so that's like 1.08. So I'll just go ahead and add those right away, to the power of x, where x is the number of years. So write an exponential equation. Oh, well, that's what we just did. So here we go. Here's your equation to represent the stock price as a function of the time in years. And then find the number of years it will take in order for it to reach $50. So basically, we're going to solve for x here, where y, or final amount, is $50. So I'm going to divide both sides by 40. 50 divided by 40 is going to be the same as 5 over 4, and 5 divided by 4 is going to be 1.25. But yeah, so 5 divided by 4 is 1.25. Equals 1.08 to the power of x. Now I can use the inverse property again to solve for x here. So I'm going to rewrite this as x equals log base and the base here is 1.08 and the power is, if this thing, oh yeah, it's 1.25. All right, and then so we should have a final answer after this because we're going to plug this into the calculator. X is approximately, let's find out. How many years do you think it will take for this stock price to reach 50 bucks? Let's find out. 1.08 and then of 1.25. There you go. About 2.899. Yeah, that's how it would round out. The number of years, this is the number of years. All right, y'all. Well, that's it for today. Let's go ahead and box this. As always, if you guys have any questions, please reach out and I'll help you out. But otherwise, y'all have a great day and I'll see you next time.